Section 6.3, graphing to solve systems of linear inequalities. We're going to look at this graph here. It says, what conclusions can you make about the system of linear inequalities? So you can tell there's one region that's all colored in, and that's the solution. Everything in here is the solution. Whoops. Everything in here is the solution. So I want to know about that solution. What defines it? So I'm going to look at this first line. I'm going to try and come up, first of all, with an equation, and then we'll figure out its inequality. So I'm going to do y equals mx plus b. This is the equation of the line, where b is the y-intercept. And in this line, I can see the y-intercept is right there. The y-intercept is at the value 3. So I can substitute a 3 in there. Now slope. What I do is I find 2 points. There's 2 points right there. I chose points that are nicely, nice points, like not 1/2 or 1/3. Okay, and to get from the left point to the right point, I have to go down 2. So I rose -2 and I ran 1. And now that is my slope. So in other words, oops, I said 3 and then I never wrote it. So in other words, my equation for this line is y equals -2x plus 3. Okay. Now, I have to look at this as an inequality. It looks like I took this line and I shaded everything underneath it. So y, this is really all the points, y is less than -2x plus 3. Now I look at that solid line, and that solid line is communicating something to me. And if you remember from last section, it says if you have a solid line, it means that there is an equal to, less than or equals to. So this is actually y is less than or equal to -2x plus 3. So that is the equation of this line. Y is, less than or equal to -2x. Okay, let's look at the other one, and we're going to do the same thing here. Y equals mx plus b. Well, the y-intercept in this one is -2, so we have y equals mx minus 2. The slope, to get from one point to the other, I rise none, and I run 1. So y equals rise over run x minus 2. Well, 0 over 1 is just 0, so this is the equation y equals 2 would be that line. But what I've done is I've taken everything above that line. I've shaded everything above that. So I said all y's that are greater than, solid line, or equal to -2. So this is my system of linear inequalities displayed by this graph. So this graph is showing all the y that are greater than or equal to 2, but less than or equal to -2x plus 3. Okay, we're going to try an example together. A company makes 2 types of boats on different assembly lines, an aluminum fishing boat and a fiberglass bow rider. So we're going to let A be the aluminum boat and F be the fiberglass boat. We have to come up with a couple of inequalities and then graph them. When both assembly lines are running at full capacity, a maximum of 20 boats can be made. So I can make at most, so I'm going to make less than or equal to 20. So this is the hardest part, is getting the language. A maximum means less than or equal to. Okay? The demand for fiberglass boats is greater than the demand of aluminum boats. And the company makes at least 5 more fiberglass boats than aluminum boats each day. Okay, this one's a little more difficult. So let's think about it. If I do fiberglass, if I did 10 fiberglass, then I have 5 or less aluminum boats, fiberglass aluminum. If I made 16, then I make 11 or 10 or 9. So you'll notice that fiberglass is always going to be related. It's going to be like it's equal to, or maybe even greater than or equal to a plus 5. Okay, because let's look at this example. If I made 16, I could make 9. That meant I meant at least 5 more, but 16 is always greater than or equal to a plus 5, because 9 plus 5 is 14. And 14 and 16, 14 is greater than or equal to. They make at least 5 more. They could make 10 more, and that would still So for instance, if I made 11, I could make only one aluminum, and that would satisfy that equation because I made at least 5 more fiberglass. Okay, so here's my two equations. Now I want to know what combinations of boats should the company make each day. So what we need to do is we need to graph these. Okay, so I have aluminum boats and I have fiberglass boats. So I'm going to let my X be aluminum and this be fiberglass. So I have to put it in a form that I can graph. And I just want you to think about this for a second. Can I make -2 boats? No, I'm only going to deal with positive numbers of boats. Okay, aluminum and fiberglass. So I'm going to solve them all just like we do y equals. I'm going to put them all in the form f equals. So this one's fine. It's this one that I'm going to change. I'm going to change it into f is less than or equal to 20 minus a. And that's just going to help us graph. Okay, so let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, 5, 5. There. So my y-intercept in this first one is 5. And my slope is 1. I rise 1 and I run 1. Rise 1, run 1. Rise 1 and 1. And I'm going to get a line that looks something like that. Okay? And I'm talking about all the f that are greater than or equals to. So I'm talking about everything above here. Okay. In this one, my y-intercept, I'm going to rewrite this one more time. And my y-intercept is 20. And my slope is -1. So I go down 1, over 1, down 1, over 1. And there I have my slope. Okay, and I have my line like that. And I'm talking about everything that's less than or equal to that. So I'm talking about everything here. So really you can see I'm talking about this region right here. But let's go back to our rules to remember how it is that we color and we show these things. So first of all, they were all greater than or equal to, but it's discrete. I can't make half a boat. Cannot do that. So how do I show things that are discrete? Remember this from the last page. When things are discrete and they're less than or equal to, it looks like I put a series of green dots and I color it orange. So that's what I need to do here, is I put a series of green dots because I'm only really including the points. I'm not including half a boat, 3/4 of a boat. Okay, so if this is being, oops, I drew that line a little wrong. That's okay. And I would take time to color in every point if I had the time, and then I would also go and color it in orange. Okay, so this is the equation, and what that means is every single point in here satisfies the boats. So let's look at this point right here. This is the point where I make 4 aluminum boats and 12 aluminums and 12 fiberglass. And I'm saying that that is a solution. So I'm saying if I went back to what I talked about, that would be true. So it says a maximum of 20 boats. Well, does 12 plus 4, is that less than 20? Yeah. It also says that I make at least 5 more fiberglass. Well, 4 plus 5, there's at least 5 more. Or 4 plus 5 is at least that, right? It's actually 4 plus I made another 8. So that satisfies that as well. So they could make any number of boats signified by all those dots there that would satisfy this system of linear inequalities. Okay, so you really have to remember how to graph lines. Then you need to go back to section 6.2 in your textbook and look at this, how to shade. This is important to do this. Let's read what they say here. When graphing, the boundaries may or may not be included depending on the type. Most systems of linear inequalities representing real-world situations are restricted to the first quadrant because values of the variables in the system must be positive. That's what I was talking about there. We can't make a negative boat. Any point in the solution region is a valid solution, but some solutions make more sense than others depending on the context. Okay? You can validate a solution by checking to see if it satisfies each, and we did that really roughly. Okay? Use an open dot to show that it is an intersection point in a system's boundary is excluded. An intersection point is excluded when a dashed line intersects either a dashed or a solid line. Use a solid dot to show that an intersection is included. This occurs when both boundary lines are solid. So you might see that in your answer key, those different dots. Okay, so you have some practice questions to try.